Last time we talked about the complex set, and I thought maybe you forgot something, and I wanna fast review of the material that we had before. We talked about the affine set, which, for example, if we have a 2-point x1 and x2, the affine set is the all x that theta x1 plus 1 minus theta x2 where the theta is one rational number, and we define the convex set is same as this one, but the theta is between 0 and 1. After that, we talked about the convex hull. It's a set of the all convex combination of the point in the S. For example, if we have a set something like this, we can define this new set as the convex hull of the original set that we had before, and we define a convex cone. The convex cone was theta 1 x1 plus theta 2 x2. For example, for the first one, if we have 2 points, the affine set is all point x1, x2. The affine set is all point on the line. The convex set x2 is all point between between these 2 points, convex hull, and the convex cone is, for example, if we have x1 and x2, it's this. Okay. And we talked about the hyperplane and half space and Euclidean balls and ellipsoids, and we talked about some norms. But before going to the new material, that is generalized inequalities, I'm gonna solve some problem to help to again remember what's the meaning of the these sets. Let's we have this question. We define a square in R2. S is x belong to R2. xi is between 0 and 1, and I equal to 1 and 2. And we have a disk D, which is equal to x belong to R2, given the norm 2 of x2 is equal, less than equal 1. Okay. And the question is, we have three sets: S, intersection of S and D, union of S and D, and S not D. we have a 3 new set, and we want to find, based on this definition, which one is the convex and which one is not. Okay, let's draw some picture. S is S is this square here, and D is the norm to of x less than equal to 1. It's circle. Okay, this one D, and this one is S. Okay, here the intersection of S and D is this area, and you can see this area is convex. The union of S and D is all this shape, and it is convex. S, not D, is this area, which is not convex. In the previous section, we, I think, convex hull, we show it with conv. For example, if this one is S, the new set that I drew is conv. S is the new set that I marked. This one is S, and the whole thing is convex. Next question is, we have a set C, which is equal to 4.10, 1, 1, minus 1, minus 1, and 0, 0. And we have again 3 questions that, for example, 0 and minus 1/3 belong to conv C. And 1/3 belong to conv C. Let's solve these two because I need to go again to the definition to write it down. First one is 0 and minus 1/3, and second one is 0 and 1/3. We have 4 points here. Let's draw a picture and see what's the conv of C. First point is 1 and 0. A. B is 1 and 1. C is minus 1 and minus 1. And D here is 0 and 0. Okay. Any suggestion for the conv of C? Conv of C is ABC. In this shape. Because contains all of the points and is convex.
So B is
Okay, now we have 2 points, 0 and minus 1/3. 0 and minus 1/3 is somewhere here. It's supposed to be 1/2. Yeah, it's a half. And minus 1/3 is some point here. And 0 and plus 1/3 is point here. Therefore, this one is true and this one is false. Okay, it's only for reminding about what we had in the previous. Okay. The other thing that we talked about in the last meeting, it was the operation that preserved the convexity. It was the intersection, affine functions, perspective, linear function, and we had some ad hoc technique to find out which set is convex and which one is not. Today, I want to talk about the generalized inequalities, but before that, we need to define a proper cone. Proper cone is a convex cone. First is convex. This convex, if we have a convex cone K, in Rn, if for having the proper cone K, the K is supposed to be closed. Solid and point. Let's see what's the meaning of each one. First one is closed. Closed means if we have a set, the boundary of set is belong to the set. For example, if you remember in the previous session, we have some sets that the boundary wasn't belong to the set, and therefore that one cannot be closed. For having a proper cone, the set is supposed to be closed. It means the boundary contains its boundary, and it must be solid. It means it cannot have some hole inside the set, and it must be pointed. It means no in the cone we cannot have any lines. Let's see if we have for example,
what do you mean by lines?
Line, if we have for example x1, and I can define for example L. I can define L. This set is convex, but in this set you can have yes, we can have some cone, not convex. It's a cone, but it contains some line here. Okay. I have, for example, this line in the R. Is it a proper cone or not? Definition of the cone says if we have 2 points in this line, any combination of these 2 points is supposed to belong to this line. Okay, therefore this is a convex set. This convex set is closed because the boundary of the this line is belong to this, but is not solid because it's in the R, and we have some point here that they are not in the R. They are not belong. They are, for example, pi, radical 2. There are some point that is not belong to the this, but because this one is not solid, and this one is not proper.
But it's pointed.
It's pointed because there is no line inside the set, but it's not solid.
So how do you define solid again?
If there is no hole in the set, there is some hole in this set.
How do you define hole?
Hole, it means some point that doesn't belong to the this point.
Yeah.
It has non-empty interior.
Okay, and that's
Yeah, it's the word of it. Yes.
I don't think it's actually the
it's not hole. It's a long empty interior that we can do with the right definition.
It's not P. P is not there because this one should be R.
Can you write in oh, okay.
But okay. You're not no hole. Are you sure about that? Like when you say no empty,
It's my understanding.
Okay.
Yes.
The definition is it has non-empty interior.
Yeah,
That was my understanding, and I said no hole. Yeah. I thought maybe non-empty interior is equal to the hole, but it's not. Because if some set has a hole, it's not convex. It's different. Okay, let's go to the generalized inequality.
Okay, can you bring the one? Okay, the previous one was.
Okay, you need example.
Yes.
Which one is? Okay.
It's a proper cone.
Yeah.
When this, how do you? That's the definition of the proper cone, or like that's the.
That's the definition of the proper code.
You bring the one example for
Yes.
proper cone.
Okay. Okay. I found 3 examples in the book. Let's see which one is. Do you remember the positive semi-definite cone? It was the collection of all matrices that. Let's go to the definition. That's part of the definition of. Okay, we had the positive semi-definite cone, and we defined that S plus N. It was 8. If any vector C multiple to the next C is bigger than equal to 0 for all C's. This was the definition of the positive semi-definite cone, and it was this one is a proper cone because it's closed, solid, and pointed. Another example is non-negative polynomial between 0 and 1, but that one needs to the proof, and it's then long to prove. It has all of these 3 points. But the simplest one is this one. The next topic is generalized. I only want to keep the title because we may need to. Generalized inequality. It's defined for a proper cone, and it says x is less than equal to the y by a given proper cone if x, y minus x is belong to the k. And there's another definition that said x is less than y if y minus x is belong to the interior of the k. Let's see what's the mean of this. For example, we want to find x is less than y by cone k if we have x and y. I select one obvious sample, x, and if we define the proper cone, this cone, we have y minus x. This one is x, this one is y. And let me see, y minus yeah, this vector is y minus x, and if I draw it from here, it's something like this, and this point is inside the proper cone k. Therefore, x is less than y by k. But sometimes we cannot say something like this if we have the same cone and we have, for example, x and y. Now the y minus x is this vector, and if you draw it from here, it's outside of the cone. Because of this, x is not less than y. And here, obviously, y is not less than x. Because if we have this vector, again, this one is outside this cone. If we have, for example, we can define this one as a component-wise inequality. For example, we can see in the x, if this x direction is y direction, in the x direction which one is less than the other, and in the y direction which one is less than the other. And there is some properties that, for example, if x is less than y by k and y is less than v by k, we know the x plus u is less than y plus v. Something that we have in the ordinary inequalities. After defining the inequalities, the next topic is minimum and minimal elements.
K distributed.
If you remember, K is a proper cone. Remember I said we can define a proper cone something like this. Okay, and if we have the x and we have y, if the y minus x, this vector, if it's inside the vector, one of them is less than the other. If it's outside, we cannot say anything.
Okay, what is K?
K is this proper cone.
Oh, okay.
The minimum set of S with respect to a proper set, proper cone K is Y for all Y equal to S if X is less than equal by proper cone K than Y. And this one is the definition of minimum element. And there's another definition, it's a minimal it says for y equal to s, belong to the s, y less than xk, y is equal to x. Okay, if we want to have an example, let's again define this one as a cone, proper cone K, and we have a set S. The point here x1, it's a minimum element because it's less than all of the points inside the S, and
Anyway, any y less than x is equal to x.
and there is nothing that is equal to x1.
And x is the minimal element also.
It's a minimum element. The minimum element is stronger than minimal element because we can define, for example, this set, and we have this point x1, and we define this cone. Now x1 is a minimal element. Okay? Because if there is something, it's equal to this one, but there is nothing.
So I mean, even if you can find just the y less than, oh, is that less? Okay, it's just less than, so less than and equal. Okay.
Yes. Okay. Let's see an example. Okay, we have a set S is equal to 0, 2, 1, 1, minus 1, minus 1. We want to know what and 2, 2 and 3, and 1 and 1. It's a minimum or mini. Minimum. Any idea?
One and one is the minimum.
1 and 1 is minimum. Okay, let's see. We have a 0 and 2. A, B, C, D, E, A. This one. B is 1 and 1. Two and 3. We have 1 and 2.
A is not calculation. A is 0 to
0 to
0
times.
A. And B is 1 and 2, yes.
Yes. And 4 and 0
C is 4 and 0.
is 0. D.
Okay.
So B is a 1 and 1.
This one is B. 2 and 3 is C. And
No, 0 and 2 is A.
it's A. And this one is B.
So B is a
What's the B?
1 and 1. It's a minimum element. No?
A is not minimum.
Oh, is it?
Because if B,
Oh, yes, A.
there is some A that they have 0, but B has 1.
Yes.
And also we have E that it has 0, but B has 1.
So A.
A and B are
A
above
is
the
the
C.
minimum.
C is not minimum or minimum.
Yes.
But A and B are minimum. Because if there is something there, we cannot compare these two with each other. For example, this one is less than the other. Because of this, they are minimum element of the set. Okay. Next topic is separating hyperplane theorem. If we have two disjoint convex set, for example, C and D, if A transpose X is less than B for X belong to the C, and A transpose X is bigger or equal to B for X belong to B, and there is an A that is not equal to 0, it's, and B that we have something like this. Therefore, all points X that A transpose x equal to b. It's a separation hyperplane between C and D. And for example, I can define the A as a normal vector equal to the. And we can have the strict here inequality.
And A and B, they are not matrix.
Yes. Okay. If you have a point that, if you have a plane that it's, we call it supporting hyperplane to a set C. A supporting hyperplane if for A transpose X is equal to A transpose X0 and if X0 is the boundary of the set and we have this one, again A is not equal to 0, and for the rest of the points that belongs to the S, we have ATX is less than equal to ATX0. This hyperplane is the supporting hyperplane. If the supporting hyperplane is on the all point of boundary of a set have this property, this set is convex.
So A can be any matrix or should be?
If there exists one A at least, because sometimes we don't have a lot of choices. But
how about that?
in this case, we have a lot of choices because we can select a lot of line different direction. But sometimes it's not. And if C is convex, then there exists a supporting plane, hyperplane at every boundary of the C. It's one way that we can find a set is convex. If we have a set something like this, the supporting hyperplane here, there is some point is less than this and some point is more than this, therefore C is not convex. Next topic is dual cone. Dual cone by definition is for a cone K, the dual cone is a set of points that y transpose x is bigger than equal to 0 for all x belong to the K. Let's draw a picture. If we have a cone K, the dual cone of K is all points that the transpose y to x is bigger than 0. It means if I consider a right angle here and this one is dual cone of K. Because all points here, they satisfy this condition. And there is some example. For example, if you have positive semi-definite cone, the dual of that cone is equal to itself, and we call it self-dual. And a dual cone is proper if a cone is proper, the dual of that also is proper.
So the cone, it should be just the line, or can it be curve also?
We define convex cone. If you remember, if you have 2 points in the 2D space,
Yes.
it was all point
Yes.
just okay. It's dependent on your space, the shape can be different.
For this one can be curve also.
What do you mean by okay? Or define the cone as this one. This is my cone.
Yes, I mean for example, if I have the cone is the curve, not it's the two line. Can I have this one and find the?
If that one is the cone, yes, you can. You can find the dual. Okay. I think I cover all of the things about the complex set. Let's go to the next topic, which is convex function. Any question? The definition of convex functions is f is from Rn or is convex if first domain of f is convex, then f of theta x plus 1 minus theta y is less than equal to theta fx plus 1 minus theta f. Okay. The domain of f is convex. It's about the sets that we talked about, and this means if we have some function like and this one is x and this one is y, any point between x and y, the value of fx plus fy is less than the value of point, is bigger than the value of the original curve of the function. For example, if we select any point in between x and y, the value of the curve is less than the value of the straight line, basically. And if f is convex, minus f is concave. define, for example, instead of using the less or equal, we can use less than, and it's strictly convex. Okay, let's do some examples. Any affine function is convex. Affine function is if you have ax plus b. For any a and b is convex. Exponential ax for any a and b is convex. Power x power a, if a is bigger equal to 1 or is less than 0, less or equal to 0, is convex. If it's rational in R. Absolute power of absolute value x for only p is bigger than 1, it's a null. It's not null. Sorry. It's a power of absolute value. And negative entropy is x. Entropy is minus x log x. And negative is plus this one, and this one is convex. Log function itself is concave, it's not convex. Okay. In Rn, A transpose x plus b is a affine function. We have a norm which can be defined as sigma of xi power p I equal to 1 to n. If p is bigger than equal to 1, is convex. And we have some complex function, for example, a spectral norm or maximum singular value, which defined as f of x is equal to norm of x to 12 x, which is the maximum eigenvector of x. This one is convex. If we have a function, but if we can restrict the function in the one line, and on that line, for any line, it's convex, the function is convex. If the domain of the function is convex, okay. One example of a little more complex function is if we have s, if we have a function f from Sn to R, then if x is equal to this function is convex. Here I can write it down the for receiving a convex function to the line, we can parameterize the function and see if the restriction based on that parameter is convex, the function will be convex. Therefore, I can write it down a function gt which is equal to log determinant of x plus parameter t and any arbitrary vector v, and I want to see this function is convex or not. I can expand this function to the form of log determinant of x plus v is arbitrary vector.
Actually,
Yes.
T is a scalar.
Yes. Okay, I can rewrite this one as x power 1 half.
How do you ensure you go all the lines? I guess that you need to ensure that for any computation of lines.
Yes, because of this I have an arbitrary vector.
But automatically, okay. Yeah.
I can rewrite this one as x power 1 half I vector plus t multiple x minus 1 half vx minus half multiple x 1 half is equal to this term, and now I can
How do you know that x is x1 half?
I want to find the symmetric expansion of this function. If I do the multiplication here, t is a scalar.
Yes, but
Therefore, I can do this one by this one.
yes, but my question is that how do you know x1 half x is
How do you
it's
have
not,
the
it's not all matrices have that square root. So what's that? So okay, your x has to be symmetric matrix.
Yes.
Okay,
Yeah.
okay, that's
Therefore, this one is equal to this one if you do the calculation, and log of determinant of this function is equal to log of x plus log determinant of I plus t x minus 1 half bx minus 1 half, and this one is equal to same plus det of x plus, for this part we have the log of 1 plus t eigenvalues determinant of the matrix is multiplication of all of the eigenvalues, and if I wanna move it to the outside of the dot, it's became sigma of summation of all of the eigenvalues.
Lambda is the eigenvalue of V.
Yes. And because the x is belong to the Sn, which is all positive semi-definite matrix, it is 0 or something positive. Therefore, whole thing is positive. Therefore, the function is complex. Any question?
Prove it.
For this one, I said true. This one is the x is the function. It's the matrix that is positive semi-definite. It's okay. If it's positive semi-definite, it means if I have any vector that multiple to this matrix, the result is positive. It's not negative. Therefore, this term is positive. Plus 1 again is positive. The determinant of this keep it positive because the determinant for this matrix is we have, for example, a matrix, and all values here are the eigenvalues if you multiply all of them, and we know the matrix is positive, semi-definite. Therefore, this multiplication is always positive. Therefore, this.
Okay, prove it is that the matrix have m values 1 minus 1 plus lambda I, which I think can you prove it? That matrix have eigenvalue 1 plus.
Okay, what's the eigenvalue of this part? Eigenvalue of this part is lambda I. Because V is a positive semi-definite, multiplication of every vector in the matrix is positive. Create a positive semi-definite matrix, and it's bigger than 0. Therefore, this part always is positive or 0. Plus 1 again is positive or 0.
Use the math formula.
Okay.
Okay.
What's the definition of
basic rules of it. Can use the property of a similar matrix to prove it.
It's okay.
Similar, you just multiply both similar matrix.
It's okay.
You can prove it more.
Okay. Next topic is extended value expansion. This is an expansion if we have a function that's it has a if you have a function f we can define a function f tilde or hat or anything which value of f hat x is equal to f of x if x belong to the domain of the f and is equal to plus infinity if x is not belong to the domain of f. And if I want to draw a picture to show it, for example, if I have a function from here to here, it's something like this, and this is the domain of f. For the f tilde, the domain is all R, but for this area we have plus infinity. And we call it extended value expansion. And if f is convex in its domain, the extended value extension is convex. Let's go to the two conditions for finding a function is convex or not, and then if we have time, we can continue, or we can solve some problem. And first order condition says if y is bigger than equal to f of x plus gradient of fx transpose on the point y minus x. The notation is clear. The first order derivation on the point y minus x. Maybe I can write as f of tx on the point of x minus, which I can define the the f of x, the alpha, the x is the from f from x1 xn, if we are talking in the R. If f is differentiable, if the domain of f is open and the gradients we can define as this vector. For each point on this domain, if we can define this one, and first order condition says for the differentiable function f, if we have this condition for all of the point x, y belong to the domain of f, the f is complex. And the second order condition says if f is twice differentiable, it means it's the first order, and the second Second of the condition says if the choice differentiation of the f of x is positive semi-definite, or is bigger than equal to 0 for all of the point x belong to the domain of f. F is convex, and if it's strictly bigger, it's strictly convex. But we keep this one as a definition.
So if the f is convex, has to have these two order, these two conditions.
If it's differentiable, yes. But if it's not differentiable, no. But if you have a function and we can have one of these two, it's I think sufficient condition for saying that it's convex. Okay. And let's go to the physical meaning of the first order definition. The first order says if we have a function, let's have a function with a slope. We have this function and we have this point, we call it x and f of x. This point here, x and f of x. And this slope is f of x. This line is f of x plus other points y minus x. It means it's we call it underestimation function. If we have this condition that for each point here the differentiation of the function multiple the y minus x plus the value of f of x is less than the value of the function, because the original value of the function is this one, but this function estimating something here. If it's less than that, it's a convex function. And this is the reason that if we have a convex function, we can find the minimum of that based on only having the first differentiation of the function. And then this one can find a global minimum. I don't know. I can stop here, or I can continue some example.